This is the video for week 11. We've used loops in Project 5 where we extended the sound effect, but we used to have to do it before the days of digital audio workstations with tape, and this is how we did it. Well, what I've done here, I've recorded on the quarter-inch tape. This is a quarter-inch machine. I've recorded a sound effect several times on this thing, but I want to take just a short chunk and make a loop out of it. Now, when I'm recording it, on this machine, I have the option of 3 speeds, 7.5, 15, and 30 IPS. And although 30 IPS is going to be the best quality, it's going to also generate the longest loop. So I'd like to have a little bit longer loop. So I did this recording at 7.5. So the first thing I'm going to do is play it. I'm going to take a grease pencil. I'm going to mark on the playback head where I want the loop to start. That's actually a good spot there. So you make a heavy white mark there. Hopefully I'll be able to see. And then I'm going to play. I'm going to stop it right before the heavy artillery goes off with the burst. Now I'm going to cut it. I'm actually placing the tape in what looks like a miter box, but this is an edit block. The brand name is Edit All Block, and I'm going to go ahead and pull this back until I find my other grease pencil mark, which I'm still not seeing because let's see. This will work. This makes a 45-degree cut, which is kind of neat because that makes the edit kind of sneak in. It's kind of like doing a fade up in Pro Tools. But take a piece of tape, and the easiest way to do this is to just attach the tape to the razor blade because the razor blade is thinner than your finger, and lay it right in the block and take your fingernail and kind of rub it off. Then I'm going to take these reels off the machine, and I'm going to put this on the machine like this. Wind it through like that. Over here. Now I need something for some tension, so I'm going to take just a 7-inch reel, and I'm going to, excuse me, put it like that. Add some tension. I'll hit play. And this will go on infinitum. We'll have birds as long as we want. Again, I could have had a longer loop. I've done loops sometimes, going across the room, using mic stands and reels there to do it. But this is kind of the short and sweet way to do it. Les Paul, who invented overdubbing and invented multi-track, also worked with tape loops. And he had a device called the Pulverizer. Here's a story about that. Pre-recorded sound has often been incorporated into live music performances. Whether it's a theatrical performance on Broadway, a theme park, a cruise ship, a corporate presentation, or a live music concert, often these performances incorporate some pre-recorded elements. Les Paul, who had pioneered so many recording techniques, also at times used pre-recorded sound in his live performances. This was especially appropriate for him since he had played all of the parts on his records by overdubbing. So to be able to control the tape recorder from his position on stage, he had a remote control that mounted on his guitar, which he jokingly called the Pulverizer. It allowed him to start and stop 2 tape recorders and also control the mix between the pre-recorded tracks, his live guitar, and a microphone that was attached to his guitar. This Chinese band invented a loop device called the Buddha Machine, and here's the story about that. Today, many performers work with effects pedals that can sample short passages and play them back as a loop. At one time, this was done with tape. Les Paul was probably the first person to perform using tape loops with his Pulverizer. Years later, both Robert Fripp and Brian Eno also performed with tape loops. In 1999, the Chinese electronic music duo of Christian Varant and Zhong Zhan, known as FM3, started performing as a chill band that would play in the back rooms of Beijing clubs. Inspired by sounds heard in a Buddhist temple, they created a loop device called the Buddha Machine. It's a small plastic box about the size of a pack of cigarettes with a built-in speaker. It has a volume control and a toggle switch to cycle through a series of pre-recorded drones that can last from 1.5 seconds up to 40 seconds. Over the years, the Buddha Machine has evolved. The newer versions include a pitch control and have some additional loops. In performances, the group does what they call Buddha boxing, where the audience is invited to participate by adding more Buddha machines and adjusting the volumes and loops to create an interactive atmospheric soundscape. You may have seen this before, but Carl Stalling, who worked originally for Disney and later for Warner Brothers as a music composer, developed the tick method, which was basically a tempo map so he and the animators could work in parallel. And the same thing is still used today. Music editors will lay out a tempo map for the composer with various on-screen actions indicated on that tempo map. Born in 1891, Carl Stalling began his career as a theater organist in the days before films had soundtracks. He would compose music for the films live at the organ several times every night. Stalling was hired by Walt Disney to score music for Disney's Silly Symphony cartoons. There, he invented the tick method, where a tempo map was created with a metronome so the composer could match the on-screen action to a particular beat. With this click track, Stalling could then pre-record the soundtrack and the animators could use his tempo map to animate. In 1930, Stalling left Disney to work exclusively for Warner Brothers, where he now had access to Warner's vast publishing catalog and could incorporate many popular songs into the cartoons. Because of Stalling's tick method, almost every on-screen action had a musical punctuation. Today, this is known as Mickey Mousing. Even though film composers still use a form of Stalling's tick method, they don't attempt to punctuate the on-screen action. That's the function of the effects track. The musical score is the emotion that the director wants you to feel at that particular point in the film. So for Project 10 that you're going to be doing this week, one of the things you may be doing is adding some echo. And when you do that, it's always nice to know the tempo of the song so that you can have the beats of the echo match up with the tempo of the song. It just sounds better when you do that. And we can figure out the beats per minute several different ways. First, you can literally just look at a stopwatch or look at your watch if you have a second hand and count the number of beats in a minute. And the important thing is to start with 0 when you're counting. You could also count the beats in half a minute and then multiply by 2, or count the beats in 15 seconds and multiply by 4. Actually, Audition doesn't care as much about beats per minute as about milliseconds per beat. And there's a relationship between the two, so if you know one, you can calculate the other. But there's a simple way in Audition to figure out the milliseconds per beat, and that's simply to isolate a beat by clicking and dragging using the time selection tool, highlighting a beat that way, and then do Command K to split it, and then just check in the Properties panel and see the milliseconds for the beat. Now, you need to be in decimal time versus time code, but when you are, you can actually see the milliseconds for that beat. You can also do this by using an app on your cell phone and mobile device. You can download these. Basically, you tap the screen along with the tempo, and it tells you the beats per minute. And in some cases, it might even tell you the milliseconds per beat. If you know the beats per minute and are trying to calculate the milliseconds, you divide 60 seconds per minute by the beats per minute to get the milliseconds per beat. Once you know that, then generally in the digital delay, you use that number for the quarter note, because that's what a beat is, and maybe half of that for the eighth note. But here's a short video about digital delay. Digital delay, like reverberation, can add a spatial quality and a live feel to a recorded track. After tape was introduced in the US in the late 1940s, engineers would use tape machines to create a delay. This was known as slapback. Acoustical delays like the Cooper Time Cube were used in recording, and longer acoustical delays were used in venues like stadiums to time delay PA announcements. These acoustical delays were simply a tube or a pipe with a speaker at one end and a microphone at the other that picked up the sound after it traveled the length of the pipe. Digital delays that are available as both standalone signal processors and plugins for workstations can now produce long delays at full bandwidth. The plug-in versions can also have the delay times linked to the song's tempo map so that the delays can be, for example, a quarter note or an eighth note or some other musical interval in the tempo of the song. To achieve the biggest stadium sound, astrophysicist and also Queen's guitarist Brian May suggested that by making the delays prime numbers like 2, 3, 5, 7, 11, 13, 17, 19, 23 milliseconds, etc., the hand claps, stomps, and vocals on their song We Will Rock You would sound like the most people, since none of the delays would be duplications of any regenerated delays. This video explains what reverb and echo are. When you stand on the rim of a canyon and yell, "Hello! Hello!" and you hear your word a second or so later, that's an example of echo. Essentially, it's the sound that's reflected back to the listener. There can be multiple reflections, as sound bounces off walls, floors, ceilings, and other hard objects. When these reflections arrive very close together, the listener no longer hears a distinct echo. This then is reverb, short for reverberation. It's what people hear when they sing in the shower. At one time, studios had rooms called echo chambers, a misnomer since they actually were creating reverb. They had a speaker that played back the sound and a mic to pick up the reflections from the room. Later, springs and also metal plate reverbs were used in studios. Tape recorders were typically used to create actual echo. The studio term for this was slapback. Today, both reverb and echo can be created digitally. When used properly, they can add a live quality to the recording and help in getting a better performance. When we used to work with tape, we had to have a track sheet because we couldn't see the waveforms, and we had to keep a record of what we had recorded. Although digital audio workstations do have a finite number of tracks, for most projects that number is so large that it's not an issue. However, that's not the case for analog recorders. Professional multi-track tape machines usually have either 4, 8, 16, or 24 tracks. Therefore, some planning and organization are necessary to indicate what's on each track, and also to assure that there are enough tracks for everything that needs to be recorded. A track sheet is usually a piece of paper which has boxes or lines that represent the number of tracks on the tape machine. They're necessary so that the recording engineer knows which tracks have content and which tracks are open, meaning that they're available for recording. They also indicate other useful information such as the recording date, the artist and track title, the tape speed, whether noise reduction was used, the producer, and the recording engineer. Often, when tracks are running low, the track sheets can indicate, for example, that the guitar solo has been recorded on one of the vocal tracks, since there are no vocals in that part of the song. When tracking or remixing, the information from the track sheet can be transferred to the scribble strip on the console, so that these operations can be better managed as well. Track sheets are unnecessary when working with digital audio workstations, since the timeline clearly displays all the information. However, for linear tape systems, both analog and digital, they're extremely useful. We talked about why it was important to name the track so that when you went to the edit window, you knew what you were working with. That's what we used to call in the old days a scribble strip. And here's the story about that. When recording to multi-track tape, engineers generally keep track sheets that indicate what's recorded on each track. These are invaluable since with analog tape, waveforms are not displayed and there's no other way of determining if something is occupying that particular area on the tape, other than watching the VU meters. Track sheets can be helpful not only to know what's been recorded and exactly where, but also to know what tracks are open, meaning that they contain no audio and are available for recording. The engineers would also transfer the information from the track sheet and generally write it on a strip of white write-on tape on the console above or below each fader. That way, the engineer could simply look at the console and know what sound was being routed through what fader, without having to keep referring to the track sheet. This information, when written on the console, is called a scribble strip. Today, both consoles and control surfaces often have digital scribble strips that automatically show the information electronically using an LED display. This can be very handy with nonlinear workstations, since the tracks and channels can change position relative to one another, and the scribble strips help the engineer know what particular sound they're controlling. This is the first project where we're going to actually have to use pan pots, and pan pots direct the sound in the stereo field. And here's the video about that. When mono signals are mixed in stereo, as is typically done in most audio mixes, the signals can be positioned not only in the left, center, and right, but also anywhere in between. This is done by using a pan pot or pan slider. The pan pot, short for panoramic potentiometer, was invented by John Hawkins and Bill Garrity when they were creating the Fanasound system for Disney's Fantasia in 1939. They wanted to be able to position the sound for the first ever stereo mix. Today, pan pots are useful for directing and also dynamically moving the sounds from left to right and throughout the room in a surround mix. On physical consoles, these surround panners are joysticks that resemble video game controllers. On virtual consoles like digital audio workstations, surround panners can be controlled by a mouse or by a control surface with a joystick. In any case, pan pots position the sound and also create dynamic effects as sound moves from point to point in the mix. There was a really popular device back in the 1970s called the stereo synthesizer. It's not what you think. It actually takes a mono signal and makes it into stereo. We're going to use something like that today to make a stereo track out of one of the mono tracks in this project. As late as the 1970s, much of the materials that were distributed to radio stations for broadcast were in mono. This included the majority of radio commercials, pre-recorded radio features, and also 45 RPM records. Just as the television industry today looks for ways to have their audio program be in 5.1 surround, the stereo FM stations then wanted to be able to broadcast stereo programming. One popular solution came from the electronics manufacturer Orban. The device was called the Model 245F stereo synthesizer. It used comb filtering to enhance certain frequencies on one side while attenuating those same frequencies on the opposite side. The result was that certain frequencies were dominant in the left while others were more dominant in the right, so that the Model 245F essentially synthesized a stereo signal from a mono source. Because the filtering was equal and opposite side to side, meaning that whatever was added to one side was removed from the other, when the two sides were summed in mono, the result was that there was no change in sound from the original mono signal. Today with DAWs, there are plugins that can do this, and it can even be done using pairs of channels with EQs set to replicate the comb filtering, which can make certain tracks recorded in mono sound more stereo. So this is a Waves plugin called the PS22, and it basically does what the Orban stereo synthesizer did. It splits a mono file into left and right. However, we don't actually need this third-party device. We can do the same thing using the EQ found in Audition. So you can see what we've done mimics the PS22 plugin where we're comb filtering in different bands. For example, because of the equalization, certain frequencies will be louder on one side than the other, and it really depends on the octaves they're in. And that tends to move the sound left and right. We may not necessarily be using it in this project because all of the amplifier sounds are probably fine the way they are, but if we had recorded the guitars with a direct box, we could use amp modeling to create the sound of the amplifier that we wanted. Like other digital signal processing, amp modeling uses the power of the computer to run programs that emulate an analog process. In this case, the DSP is used to produce the sound of a specific guitar amp. The first step in creating the software program is to find the actual amplifiers that are to be modeled. They need to be totally functional and a good representation of those particular amps. Signal is run through the amplifiers, and the output is measured. This process is repeated using multiple settings with all of the various parameter knobs on each of the amps. Once all of the data has been collected, the software engineers write a program so that the DSP will produce an emulation of the sound of each of those amplifiers that also changes appropriately as the various knobs are adjusted by the user. The software engineers also develop a graphic user interface that has the look and feel of the actual amplifier that was modeled. Players can simply use a DI, direct insertion box, for their guitar and let the plugin create the sound of the desired amp. The sound of the amp can then be adjusted at any time during the recording, even during the final mix. And since for most projects we don't have the luxury or the time and budget to send the final files to a mastering engineer, we end up doing a lot of our own mastering. So this is an episode about what mastering is. After a group of songs has been mixed and before they get replicated on CD or other media, generally the material is sent to a mastering engineer. The mastering engineer looks at all of the mixes and makes adjustments to the frequency spectrum with EQ. They also adjust the volume and dynamic range of each track with compression and limiting. Both of these steps make the songs seem as though they were all recorded and mixed in the same session. In fact, a group of songs that might make up a CD could have been recorded over a period of time in several different recording studios using a variety of recording engineers. Usually it's a more pleasant experience for the listener if the CD sounds tonally and more dynamically consistent from first track to last. Mastering engineers use both their ears and technical devices like real-time analyzers to check the frequency balance of each track. They use their ears and can also look at amplitude waveforms to determine which tracks need volume adjustments and more or less dynamic compression. Generally, mastering engineers prefer that the mix engineers do little or no program limiting, since this leaves the mastering engineer fewer options. Here's an example of a record that I had mastered. It starts out with the original sound of the recording, and then it switches over at some point to the mastered sound. And you can hear that it actually sounds better later on after the mastering was applied. Composer Rob Potter posted this on his Facebook site after one of his movie soundtracks got mastered, and he was really pleased with the way it turned out. He said it was like the difference between a short order Cook and Wolfgang Puck. And I've had that experience as well when I get tracks back from a mastering engineer. It's like, wow, they sound great. Basically, they're just louder. That's why we like them, but they do usually sound better. Artist Neil Young was kind of bummed with the sound of MP3s, so he came up with a new device called the Pono Player, and here's the story about that. When Dr. Karl-Heinz Brandenburg invented the MP3 format in 1988, MP3s sounded comparable to the 44.1 16-bit CD files they were meant to replace. However, since most music today is recorded in studios at higher sample rates and bit depths, typically from 96 to 192 kilohertz and at bit depths of 24 to 32 bits, Neil Young and other recording artists have complained about how the end user hears their music as MP3 files. So Young has proposed a new type of music player called the Pono Player to present songs as they first sound during studio recording sessions. The name Pono, which rhymes with phono, is actually a Hawaiian word meaning righteousness. The Pono Player will play 192 kHz 24-bit FLAC, free lossless audio codec files, which are about 50 to 60% of the file size of the uncompressed PCM files. Unlike MP3 and AAC files, all of the data is preserved due to the lossless compression scheme. The industry had previously moved in this direction with the introduction of the Super Audio SACD introduced in 1999, but had lost the war to iTunes, iPods, and MP3s in 2001, since consumers had chosen cost and convenience over quality. It'll be interesting to see how many people will spend the estimated $400 for the 128GB Pono Player and purchase music downloads in that format, which will average about 36 megabytes per song, as opposed to 1/8 of that file size for a typical MP3. The basic idea is that if you start with really high quality digital sound, it may actually sound better to be able to reproduce that same thing. But a lot of the material that's being created for the Pono Player actually comes from analog tape or comes from vinyl records, where there's not that much high frequency to begin with. And so the result is just about the same whether you're listening to an MP3 or the Pono Player. Just like after the iPod came out, there was the Zune. This is an ad I saw for another high-res audio player called the Fio. It was normally about $400, but it was on sale for about $180. I've seen others as well. Personally, I don't think people really want another device to carry around. I think everybody's happy hearing everything on their mobile phone. This is a video showing a recording engineer hard at work. And we do work hard at times.
It's dramatic. We're not going to make it. We'll never see the light again. But I will keep on going till the end. Yeah, 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 yeah. Our ship has faced a hurricane, but I will keep on going. My soul will sing, and I will keep on going
Obviously, that was a parody of Auto-Tune. Here's the story about Auto-Tune. Auto-Tune is a trademarked product of Antares. However, it was originally created by Exxon engineer Andy Hildebrand, who was researching methods of interpreting seismic data. He realized that the same technology could be adapted for audio recording to detect, analyze, and retune a musical note. In addition to subtle pitch correction, much of what people associate with Auto-Tune today is an effect that was used on Believe, a 1998 recording by Cher, and is now widely known as the Cher effect. When Auto-Tune is used this way, it turns musical scoops and bends into discrete steps, and also allows only certain pitches to be reproduced. This transposes singers' voices to these predetermined pitches, and frequency shifts those harmonics in the process, producing a mechanical, robotic-sounding vocal track. Since 1998, many rock, pop, R&B, and hip-hop artists have used this effect in their recordings. Okay, that's it for this video. Go ahead and look at Project 10.